FYI. All right, let's get started. We've wasted too much time. Wasted? It's kind of a stretch. All right, we start chapter 8, section 2. So this is it. This is the beginning of the really, really meaty part of chapter 8. It looked like the nose had it, huh? It looked like the nose had it. Okay, here we go. So I have intentionally not shown you too many animations when it comes to sequences, but I have some that will kind of illustrate what's going on here. So this is an example of a sequence that converges. So the sequence, you can barely see it up there, is the sequence A sub n is 1 plus n over 3 plus 2n. All right, so this sequence converges because if you take the limit as n goes to infinity of this, you'll wind up using L'Hopital, you'll get 1 over 2, so it converges to 1/2. So you can see with the black dots is the sequence, right? And obviously the values of those are approaching 1/2. The red is what that sequence would look like if you graphed it as a function of x. All right, but we can change that sequence around. We can pretty much put whatever we want in here. So let's do something like, let's do an alternating sequence. So let's do, whoa, what the heck? Let's do -1 raised to the n. And let's divide that by n. Why is it not taking that? Okay, I need to reevaluate this code. Hold on, there we go. Okay, -1 raised to the n, divide that by n. Where the hell's my sequence?
Oh, it's tiny. You can see it just really
Okay,
small.
oh, here we go, point size. There they are. Okay, there we go. So that's an example of the sequence 1 over n, I'm sorry, -1 to the n over n. So that's what you were saying, alternating. Just because it's alternating doesn't mean that it doesn't converge, right? It could. That's -1 to the n over n. So that converges. If we go out further, that's only the first 25 points in the sequence. If we go out to like 100 points, you know, now you can really see it's converging to 0, right? Okay? So when we talk about the limit of a sequence, we're talking about what the values are approaching, right? Just like a function. I have another one to look at here. Sine. This is an interesting one. The sequence sine n.
That's pretty.
It's really just completely random, isn't it? I mean, it almost looks random. This is the sequence sine n. And you can see that obviously it's not converging. We could go out pretty far in this one. You're never going to have any sort of... It is kind of, you do kind of get a little pattern to it, but it's obviously not converging, right? Let's see if I have any other interesting ones. Okay, we talked about this one. This is really cool to look at. Remember we talked last class about this one, r to the n? And we said, for what values of r does this one converge or diverge? And we came up with like a list that showed when it did. So what I can do here is I can illustrate that by changing the value of r. Right now, I have the computer having r being 0.5, and it should converge. And you can see it, right? It's converging. But let me change the value of r. So if I make r, let's see, still converging, right? R is now, if r is negative, it still converges, right? Let's see, when is it going to start to diverge? See, look, with r being negative, right? When does it start to diverge? When you get to 1, right? Ooh, and once you get past 1, look at it. See it? The other way, if r gets bigger than 1, it starts to diverge out.
So it's between -1 and 1.
Yeah, but there was some, like if it's equal to 1, then it converged, but if it's equal to -1, it diverged. So, yeah, so that's kind of cool, right? To see that in action. See that one's, yeah, that one's no good. Okay, so now we begin series. All right, series 8.2. So given a sequence, A sub n, we define a series as follows. What it is, a series is just the sum from, I'll use n equals 1 to infinity of A sub n. Now this is an infinite series. So what is this? So you remember this notation, right? This notation means you're going to add things up, right? You're going to start with n being 1, and you're going to stop never, right? So this means I'm supposed to add up starting with 1, right? A sub 1 plus A sub 2 plus A sub 3 plus forever and ever. This is an infinite series. So basically, it's the sum of the sequence. You know how the sequence was just a list of numbers? Right? This right here is just A1, comma, A2, comma, A3, comma, and it went forever, right? This is just add all those up. So take this one, add it to that one, add it to that one, add it to that one, keep adding them up forever. And that is called the infinite series that goes with that sequence. So sequence is a list. A series is the sum of the list. It's that simple. Does that make sense? Just the sum of the list. The problem is it's an infinite sum. So, what does it equal? Now, let's take a look at some examples before we get into more definitions here. As an example, let's take this sequence, 1 over n. That sequence written out is 1, 1/2, 1/3, 1/4, forever, right? That's the sequence. What is the infinite series that goes with that sequence? So what is the sum is n equals 1 to infinity of 1 over n? Well, that's 1 plus 1/2 plus 1/3 plus 1/4 plus forever and ever, right? That's what it is. So the question becomes for us, is this sum finite or not? Meaning if I add these up, does it blow up and become infinite or does it not blow up? In the event that it blows up, we're going to say it diverges. In the event that it doesn't blow up, we'll say converges. But I'm getting a little ahead of myself. I just want you to understand what the series is just the sum of the sequence. Now, before we can proceed and get further into this, we need to define something called partial sums. Partial sums. So given a sequence A sub n, the kth partial sum the kth partial sum, that's what we're calling this. The kth partial sum is defined to be this, is the sum n equals 1 to k of A sub n. So what does the kth partial sum really mean? How is it different than this series, the infinite series up there? It stops. It stops at k, right? It stops at k. So that means it's going to be A sub 1 plus A sub 2 plus A sub 3 plus, and you keep going, but this time you stop at A sub k. That is what the kth partial sum is. And I should also point out to you that this kth is a dummy variable. So if you said, what's the mth partial sum, then this would be sum n equals 1 to m. Or if you say, what's the pth partial sum, you could do this to p. Jth partial sum. So it's a dummy letter, basically. But kth is usually used. All right? Got it? Okay, so pay attention to the next part. Super, super critical. Moving ahead. If that's the kth partial sum, then I want you to take a look at this. Get rid of this example. Given any sequence, A sub n, define a new sequence as follows. I can't spell. Okay, so if somebody has a sequence, all right, I'm going to generate a new sequence from that sequence, and here's how I'm going to do it. The new sequence is going to be defined this way. S sub k is equal to sum n equals 1 to k of A sub n. I know that's a little tough to look at at first, but let me go through and show you what this sequence is. All right, so I'm going to define this. So I'm defining a new sequence. So what is the first number in my sequence? What is it? It's the sum as n goes from 1 to 1 of A sub n, right? So what would that be? Just the first, it's the first number in this sequence, right? This is A sub 1, A sub 2, A sub 3, comma, dot, dot, dot. That's the sequence I'm starting with. The new sequence I'm generating, the first piece of it, the first number in it is just that first one, A sub 1. What's the second number in this new sequence? It's the sum as n equals 1 to where now? To 2 of that sequence. So it's the sum of the first 2 up there, right? So this is A sub 1 plus A sub 2. What's the third number in this sequence? Sum of the first 3, right? What's the fourth one? Sum of the first 4. What's the fifth one? Sum of the first 5, right? So I've just taken a sequence and I've created this new sequence which adds up the terms or the numbers within that sequence. Agreed? Okay. But do you agree also that this S sub k, right? This right here, S sub k, is just another sequence? I mean, it's just another list of numbers, right? But the thing is, they're not these numbers, right? It's like these are the same, but this one is those two added, this one is those three added, this one is those four, right? But at the end of the day, this is a new sequence, isn't it? And what do we ask ourselves about sequences? What did we ask ourselves about sequences last class and on your quiz? Do they converge, right? Do they converge? We saw sometimes they do, sometimes they don't, right? Sometimes they do, sometimes they don't. So that's the ultimate question for us right now, is does this sequence converge? If it converges, that means that adding all these up goes to something. If this diverges, adding all those up doesn't go to something. Does that make sense? So going back to the definition I wrote on the board earlier, this all has to do with partial sums in this new sequence. Given an infinite series sum n equals 1 to infinity of a sub n. Okay, that's where we started this whole topic with, right? Let's add up everything in a sequence, all the numbers in a sequence. Right there, that right there. Let's say we're given that. We will say the sum converges if the limit as n goes to infinity of s sub n converges. That means we're going to look at this right here, and we're going to see, does this sequence converge? If this sequence converges, whatever it converges to is the value of that infinite series. All right. I know this all seems weird at first, okay? And we're going to need to get to some examples for you to be able to kind of clarify things. Also notice that if I change this to k and that to k, it's the same thing, right? So we kind of interplay these indexes. They're all dummy variables. It doesn't matter what you use there. Yes? I think I did, didn't I? No, I'm pretty sure I did, because there's a red light.
I don't know.
Yeah. Yeah, no, I'm glad you mentioned that. Yeah, I did turn it on at some point. Okay. All right. Let's take a look at some of these visually first. Let's take a look at that 1 over n. Okay, so what I have here, this is 1 over n. On the left side, what you're seeing is the sequence 1 over n. So this is the sequence of numbers 1, 1/2, 1/3, 1/4, right? That's what you're seeing plotted over here. And obviously, the sequence converges to 0, right? Now, what you're seeing over here is the new sequence that I generated, which is actually the sum of those things. So this sequence, what's the first number in this sequence? 1. What's the second number? 1 plus 1/2 or 3/2, right? What's the next number in the sequence? 1 plus 1/2 plus 1/3, right? Got it? Next one is 1 plus 1/2 plus 1/3 plus 1/4. And you can see that this sequence obviously behaves much different than this sequence. Yes? The question is, does that converge or not? Because if it converges, that means that the sum of all of these is finite, as opposed to being infinite. Now, what do you think from the look? Does it look like that sequence converges? We know this one does. Does it look like that one converges? It looks like it's getting bigger and bigger. Now, it's hard to say. Maybe there's like a horizontal asymptote up here. Maybe it flattens out. So maybe I can go out some more. Let me go more points. So I'll go further out. Take a look at what, see, I have what this is converging to right now. So I'm adding up right now the first, that's the first 25. So I've done 1, the next one is 1 plus a half, and I've done this to the first 25 numbers, and it's adding up to be 3.81. So as I add more numbers, that number, see, it grew to 4, 4.3. It's growing, right? It looks like it's taken off, right? Let me go out further. Let me do the first 400 numbers. Still growing, right? It's slowly, but it is growing, right? So these points are a little too big. I'm starting to slow my computer down. Let's go out the first 800 numbers. It's trying, right? So it is growing, right? I mean, we're still kind of on the fence though. Like maybe it does flatten out, but it appears to be growing. It appears that this sequence diverges, right? This one converges, but the sum of the things diverge. It appears so, yes? Let's try something else. Let me back this up because there's way too many points. Instead of 1 over n, why don't we do, how about 1 over n squared? What do you think? Going to get the same property or not?
Probably, but much bigger, but much quicker. It'll accelerate a lot more.
Okay, check that out. So remember, this sequence over here, this is 1 over n squared. So the first number is 1, right? Then 1/2 squared, 1/4, right? Then 1/3 squared, 1/9. Yes? 1/16. So this is obviously converging to 0, 1 over n squared. But what about its sum? What does it look like is happening? Almost the same sort of thing? Is it? Let's see. Let's go a little further out. I don't know.
Looks like it's approaching 2.
That seems like it's flattening out, doesn't it? It doesn't seem like it's growing the way the previous one was. It's like it's just, it almost seems like it's like capped out somewhere, right? So 1 over n appears that the sum grows, but 1 over n appears that this sequence grows, but 1 over n squared, it appears that this sequence right here kind of gets capped out. Yeah? So our goal for the next few weeks is for me to give us a series, and for us to figure out whether or not it does this, flattens out, or blows up. Okay? So students have problems sometimes with this idea. And so let's resolve this real quick. And we may have talked about this already. If I have a series, an infinite series, we know this is a1 plus a2 forever. If I tell you that each of these are positive numbers, and I'm adding up a bunch of positive numbers forever, students will have a problem with the idea that this could ever converge. Like we talked about this pouring the liquid in. I thought we had this conversation. No?
The iceberg conversation?
No. No, I have this, yeah, I don't know, maybe it was. But I didn't do it in here? Okay, we should do it. We get this idea, a lot of students have, and it's a very logical idea, that if I take a positive number and add another positive number and add another positive number, and I keep doing that forever, like how can that ever be finite, right? That seems kind of counterintuitive. But I have an easy example to show you that it's possible. So if you have a container that holds like 1 cup of liquid, and this is all theoretical, a perfect container, 1 cup. what would happen if I take and I pour into it 1/10 of a cup? Okay, so I pour that in. Here it is. I got 1/10 of this cup is full. And now I come in after that and I add 1/100th of a cup. So I pour in 1/100th of a cup, and now the water levels come up a little bit, right? And then I do 1/1000th of a cup. Pour that in, water level comes up a little bit more, right? And I keep going forever. The question is, does it overfill the cup? So what do y'all think? No? So what's your argument that it does not? These getting smaller? So because they're getting smaller, it won't fill up?
I mean, it would take years and years and years. Eventually, you're getting down to the molecular level and the atomic level. Like, it's never
Theoretically,
gonna fill it up.
this is theoretical. So forget atomic level. Imagine that we could keep going smaller and never run out, okay? So this is purely theoretical. No evaporation. This is a perfect container. Obviously, there's no such thing as a perfect container with 1 cup exactly volume, right? But in theory, would this overfill? So one argument is no, because these are getting smaller, okay? And the other argument is that eventually it will, because you're adding forever. Any other sort of arguments? So let me challenge the idea of it getting smaller. Okay, would this... Same idea. 1 cup, I pour in a half, then a third, then a fourth. Will that overfill? Yes? But these are getting smaller.
Decrease at a fast enough rate.
Okay, so that I needed that. This, you're saying they're getting smaller, but they're getting small really fast.
Too small of a rate.
This right here is getting smaller, but not small fast enough, right? I mean, think about this. This would fill it up half the way, right? What would these two together be? Put those together, a common denominator. What would you have here? This would be 7/12 if you put those together. That's more than a half. You're already over. You already overfilled the cup. Just on the first 3, boom, it's overflowing. So you can't make the argument that just because these get smaller, it won't overfill. It's that they're getting small really fast. Now, but I'm still not convinced that it doesn't overfill, though, right? So how do we convince ourselves that this doesn't overfill? Well, there's an easy way to show it in this example. Watch. This is the decimal point 1. This is the decimal point 0.01. This is decimal point 0.001. And that keeps on going, right? So if I put these two together, what do I get? 0.11. Then if I add that one to it, I get 1. Next one, 1. Next one, 1. Right? Forever? And that's actually the fraction 1/9. If you just do 1/9 on your calculator, you get 0.111 forever. So if you were to do this experiment, pour in 1/10 of a cup, 1/100th of a cup, 1/1000th of a cup, and do it forever and ever and ever, amen? You actually would be asymptotically approaching 1/9. Like if you ever stopped pouring, I can tell you you're really close to 1/9. You're not quite there though. And if you poured the next one, you would be even closer to 1/9, but you would never go past 1/9. So not only would you not fill the cup, you would even fill it up halfway. Make sense? Now you can't argue with that unless someone wants to tell me that these fractions aren't these decimals. Yes?
How do you start with 1/10 and you're only approaching 1/9?
1/10 is smaller than 1/9.
Oh, just
Yeah, it's okay.
kidding. I was like, wait.
It's okay. Yes? So, big picture. It is possible to add up an infinite number of things and still have a finite value. We have to take that into this. But it is also possible to add up an infinite number of things and have it overfill. Right? Make sense? Okay. So we have just kind of, yeah, all right. We have a quick way to check if a series diverges. We do have a very easy way to tell if a series diverges. All right? And it's called the nth term test. And here's how it goes. If you're given an infinite series, if the limit as n goes to infinity of a sub n is not equal to 0, then the series diverges. Okay. I'm going to show you this with an example, and then hopefully all that will make sense. In your formulas that you're allowed to have on tests, right? You're allowed to have some formulas on your test. I'm going to go, I had them printed for me. Let me go grab a couple of them for you. Okay, I don't have one for everyone, but I think I have enough to put 2 at each table. These are on your, yeah, these are on your, yeah, you've got it there. Right here. May not, at least one for each side, yeah. Let's see. Maybe y'all can share that. Yeah, here, can y'all share that? I don't have enough for everyone. So this, what you're looking at here, all right? I said the main goal from here on is to figure, given a series, is for us to determine whether or not it converges or diverges. And this is a summary of all the different things that we might have to do to check to see if a series converges or diverges. These are called, or this is called, the summary of convergence and divergence tests for series. All right? You can have this on the test. You're welcome. I had to memorize these when I was a student, okay? I had to know these tests. So you have to, you're going to have the ability to reference them. The first test on this list is called the nth term test. There it is right here. It says if the limit of this thing is not 0, then the conclusion is that, what? It'll diverge, right? So let's see this as an example. As an example, let's look at this series. Sum n equals 1 to infinity of n plus 1 over 2n plus 1. I put a couple of copies. I didn't bring enough. This is off the form. This is off the website.
Oh, good.
So if you have those printed out, they're there.
Okay.
Yeah. Okay, so let's look at the notation first. We are looking at a series, right? N starts at 1, ends at infinity. Here's the sequence, okay? So this is that part, right? That's your a sub n. That's your a sub n. What we want to know is, does this thing converge or diverge? So the first test we could run is this nth term test. We're going to take the limit as n goes to infinity of that, n plus 1 over 2n plus 1. Now we already know from our experience last class that this thing goes to a half, right? We could do L'Hopital and we'd figure that out, right? This goes to a half. So this goes to half. And because it goes to half, and that 1/2 is not 0, right? Then what can we say? That diverges. And we're done. This series is like the pouring the liquid into the cup. The cup overfilleth. How did he say it? The cuppeth overfilleth. Runneth over, okay? That's what's happening, okay? It overfills. Got it? Super easy test, right?
This works for series, not sequence, right?
That's right. This is a test for series. Now, you have to be careful with this test. Let me give you another example. Oh yeah, this test is always the easiest, but it is the easiest, but how about this one? Okay. Okay, let's run the nth term test first. It's the only test we have at this point. So does this thing converge or diverge? So I do the limit as n goes to infinity of 1 over n, and what's our answer? Is 0. Okay, what does that tell us?
Convergence.
What does the chart say? Inconclusive. So look, all the nth term test says is this. If this limit is something other than 0, you're guaranteed divergence. Okay? It's a test for divergence. It does not test for convergence. If you take the limit and you get 0, guess what? You don't know anything. All right? You don't know if it diverges or converges. You still don't know anything. Okay? So the test fails. It's like a bad pregnancy test. You just throw it out. It's a bad test. Okay? It's a defective test, essentially. Right? So you go to the next test. Yeah. No, you buy 4 different brands, just to be sure. You get the idea, right? It's a failed test. The test only tests for divergence, and it only works if you get something other than 0. Got it? Somebody on the test is going to do this. They're going to do that. They're going to do that. They're going to say converges, and I'm going to take every point off that I possibly can because that is a just fundamental misuse of the test. This series would be super easy if that's all you had to do. Take the limit. If it's 0, converges, not 0, diverges, be done. No, it just doesn't work that way, unfortunately. Because 1 over n, remember when we looked at the picture of it, it looked like it was growing, but then when we tried 1 over n squared, it looked like it flattened out, didn't it? But they both go to 0. So it doesn't tell you anything. It's just when it goes to something other than 0. All right, now we are going to get into that deeper. But before we get into just arbitrary series, how am I doing on time? Oh, wow. Before we get to arbitrary series, because ultimately we want to I hand you a series and you figure out if it converges or diverges, and you use these tests, all right? But before that, there are 3 common series that we must be familiar with. The first is called a geometric series. The second is called a harmonic series. And the last is called a telescopic, or it might be called collapsing. Series. So we want to get to a point where if somebody were to present us with one of these three, we'd be able to kind of look at it and be like, oh, that's a geometric series. Oh, yeah, oh, that's a harmonic series. We just want to be like familiar with it. So we're going to start with geometric. Let's see how far we get with what's left of the class. Okay, I think we can maybe get through geometric and harmonic. Telescopic, we'll have to wait till next time for sure. So we'll start with geometric. Okay, so geometric series. A geometric series looks like this. Sum n equals 1 to infinity of a times r to the n minus 1. Here a is a constant. So a is an element of the real numbers, and obviously a is not 0, or else this thing would just be zeros, right? And r is also a real number, okay? So we have two real numbers. Let's take a look at what this series looks like if we started to write the terms out, okay? Let's write the terms out. What would be the first term of this sum? So you replace n with 1, so you get a times r to the 0, which is just 1, that's 1, so just a here, plus a times r to the first power, right? Plus a times r squared plus a times r cubed plus dot, 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 right? Forever. Agreed? This is what a geometric series looks like. It's always a constant. Every term has the same constant in it. And then the number next to it, or the factor next to it, is always something raised to powers that keep getting bigger and bigger and bigger. All right? Yes? Yes? Here's an example, real quick example. 1/10 plus 100 plus, I need to add a 1 onto the beginning of that. 1 plus 1/10 plus 100 plus 1,000. Look at that one right there. That's a geometric series. Now, it might be hard to see that right now, but let me help you see it. First, can we rewrite all these as powers of something? So this is 1 plus, can I rewrite this as 10 to the negative 1? Or sorry, let's not do it that way. Let's write it this way. 1/10 to the positive 1. What is 100? 1/10 squared, what's 1,000? 1/10 cubed, right? Plus, and then it would keep going, yes? Do you all see that this is geometric? What's A? A is 1, right? A is 1. And so there's a 1 in front of all these, right? So here A is 1. And what's R? R is 1/10. Do you all see that example? Okay, I just wanted to show you an example before I proceeded. The question becomes now, does a geometric series converge or diverge? In general, do they converge or diverge? And the answer is it depends. It depends on R completely. All right? This number right here is going to determine whether or not this converges. In this case, R is 1/10, and it will converge. But I need to get to that. I need to show us how. So check this out. See if you like this or not. What I'm going to do first is this. I want us to look at S sub k. So what is S sub k by definition?
Sequence. Or a series, excuse me.
Yes?
Like
It's the sum of the first k terms, right? So this is the kth partial sum. We defined that earlier. This would be a plus ar plus ar squared plus dot, dot, dot. Where do I stop? Ar to the k. All right. So I need to state this here. Does this converge or diverge? Right? That's what we're trying to figure out. Does it converge or diverge? I'm about to show you what it does. What I'm about to do is not something you would do, you come up with on your own. All right? It's something that someone else figured out. All we're going to do is use the result at the end of this, all right? But it's very, very clever what they do here. Okay, so that's the sum of the first k, right? That's what it looks like? Yeah? Hold on. Just a second. What's that last one? Be careful. What's that last one? That last one is not r to the k. What is it? K minus 1. Remember, when you plug in 1, you get 0. When you plug in 2, you get 1. When you plug in 3, you get 2, right? So when you plug in k at the end, your last one is k minus 1. Right? Up here? Okay. Still want to know what this is, right? We want to know what this sum is if you do it forever. So now what I'm going to do, I want you to take the kth partial sum, and I want you to multiply it times r. Why? Because it's going to work. Watch. Multiply by r. So what's a times r? AR. What's the next term? AR squared. What's the next term? AR cubed. Plus, all the way down to the very last one. What's the last one? AR to the, just k this time. Just k. All you're doing here is adding a factor of r to each of these, right? That gets an r, that becomes r squared, r cubed. And then this one gets another r, so that k minus 1 becomes just k. Do you all agree with those two lines? Yes? Sure? Okay, now I want you to do some algebra. I want you to tell me what s sub k minus r times s sub k is. What would happen if you took this and subtracted this? Okay, take that line and subtract this line, and what would happen? So what would go away? These would go away. These would go away. Next one. Next one. Would this one go away? The very last one would go away with the one in front of that, right? So what would you be left with? The a from up here and minus this one, right? So a minus ar to the k. Y'all still there? On the left side, I want us to factor out s sub k. And lastly, I want to isolate s sub k, so I want to divide by 1 over r, or 1 minus r. All right, I want you to pay close attention to what I just did here. The beginning of the question was saying, what is the sum of this thing if you go forever, right? That's what we want to know. If you go forever, does it add up to something or not? So what I did is I said, let's look at the kth partial sum. Let's look at the sum of the first k. Here's the formula for it, right? The sum of the first k is this, plus this, plus this, plus this. But then I did all this weird stuff, and what I did is I came up with a new formula for s sub k, didn't I? But notice this new formula for s sub k doesn't have this, plus this, plus this, plus this, right? It's just this nice, compact, tight little formula, right? So what I'm going to do now is check to see if this sequence converges or not. And how do I check to see if this sequence converges or not?
Take the limit.
Take the limit, as in this case, as k goes to infinity. Right? I'm going to take the limit as k goes to infinity of this. So what is the limit as k goes to infinity of s sub k, which is the same as limit as k goes to infinity of a minus ar to the k over 1 minus r. So what is that limit? You're going to need something from last class. No.
Or you said it equal to a function of k.
K is going to infinity, right? The denominator doesn't have a k in it, right? That doesn't have a k in it. The only thing that has a k in it is that right there. This right here. What does r to the k do if k goes to infinity? Depends on r. It depends on r. Didn't we do that last class? We went through the whole thing. We said, well, if r is 1, what? it converges. If r was bigger than 1, it diverged. If r was between 1 and negative 1, it converged. And if r was negative 1 or less, then it's divergent. So we went through that whole thing last class. We did. I know we did. I was here. Okay? So what we can determine here is that for this, right, for this situation right here, if the r is here or here, what will it do? It converges, right? Right? In fact, what did it converge to? I want you to look back. You're going to have to look back on your notes from last time if you want any help with this. When we were last class, we looked at the limit. I think we used n. N went to infinity of r to the n. And we said there were a couple of cases. Like if r was between negative 1 and 1, what happened? Like if this number is smaller than 1, less than negative 1, it converged, but they get smaller and smaller and smaller as you raised them to power. So that would converge to 0, right? So if this is true, then that limit would go to 0. Yes?
Are those cases diverges when r equals 1?
What? Oh, no, okay, but hold on. Nope, you're on the right track. Hold on. Not the series. Okay, I'm looking at the sequence right now, right? This sequence will converge to 0, right? Will converge to 0 if our r is between negative 1 and 1, right? It'll converge to 0. Now, what if r is 1? If r is 1, this thing is just 1. This limit as n goes to infinity, r to the n, converges to 1. It is 1. It's 1 to any power, right? And then what about if it's anything else? It just gets huge, right? So if r is between negative 1 and 1, this thing goes to 0. If r is 1, it goes to 1. Any other situation, the thing blows up, gets huge. Yes? So come back over here. This sequence we're looking at, this piece right here. If the r is between negative 1 and 1, right? If we take this out, what can we say would happen? If the r is between 1 and negative 1, that thing goes to 0, doesn't it? So what would that go to? So if r is between there, then the limit as k goes to infinity of a minus ar to the k over 1 minus r would go to what? Because that's going to go to 0, right? So that kills that whole thing off, and what are you left with? A over 1 minus r.
So one more time, how did ar to the k become 0?
Because I'm saying if we're looking at this, and if we say that the r is between negative 1 and 1, then from last class we know that if r is between negative 1 and 1, then this limit will go to 0. So that limit's going to go to 0. So that kills that off, and all we're left with is a over 1 minus r. Now, what if r is not this? What if r is negative 1 or 1 or anything else? It's going to blow up, right? It's not going to converge. So you say, else this thing converges, diverges. Diverges. Which is what the second thing on your test says. Let's read through this. Geometric series, right? When does it converges with the sum of s equals a over 1 minus r, this, so long as the absolute value of r is less than 1. which means this. That's what this means. The absolute value of r is less than 1. If the absolute value of r is greater than 1, that means you're outside this interval, then you are diverging. Now, so you don't need to know where this all came from. You just need to know how to use it, but it's nice to see where it came from, right? It's not just falling out of the sky. So let's do a problem. I got the same look on my students' faces earlier today. I don't know if it's just getting to be that time of the semester. But I will tell you, I mean, I've been warning you of this the whole time, like chapter 8's coming, right? And the problem with it is we're all tired, we're ready for the semester, Thanksgiving's around the corner, and the class is about to get as hard as it's gonna get, So even though you're like, you gotta find a way to,
There's a lot of new stuff.
yeah, it's new, I'm just trying to encourage you because I see a lot of very lethargic looks. You got to go do some push-ups in the hallway or something, drink a couple of Red Bulls, Okay, you ready for an example? Let's do an example. Find the sum. All right, when you are looking at a problem that involves a series, if you are asked to find the sum, okay? You are most likely looking at a geometric series or a collapsing series. Generally speaking, it's difficult to find the sum of an infinite series. We can tell it converges or diverges, but finding the actual sum is not easy. So if you're asked to find the sum, you should assume that it's either geometric or collapsing, because those two we can find the sums of. So that's a key indicator on a test. If it says find the sum, you're either geometric or collapsing. All right? So find the sum of this series. Let's do it. 1 plus, no, not 1. I want to do 1/10 plus 1/100th plus 1/1000th plus ... Okay, now we already know the answer to this. What's the answer? 1/9. Okay? It's 1/9. But we're not going to do it with the decimals because that won't work later, all right? So we first need to see it's a geometric series. Okay? So I'm going to rewrite this as 1/10 to the first power plus 1/10 squared plus 1/10 to the third plus. So I have to recognize that. I have to see that, right? And now what I'm going to do is I'm going to try and rewrite this. I'm going to try and come up with the formula for it. Okay? So what is the formula that would generate this as a sequence? Like if I was trying to generate this list of numbers. This is what your quiz was earlier today, right? I gave you a list. If you were trying to generate that list of numbers, because this is just adding them up, right? What would be the formula that would create that? 1/10 to the n. So I'm going to rewrite this as sum n equals 1 to infinity of 1/10 to the n. Follow? Yes? Now, geometric series look like this. Super critical here. This is what the formula looks like on your sheet. Right? A times r to the n minus 1. Is that what we have right here? Do we have a number sitting in front of this, r to the n minus 1? We don't have that, do we? We don't? But we can make it happen. So we've done something like this back with integrals. Watch. Just watch me do it this first time. Sum n equals 1 to infinity. I really want it to be what? I really want it to be what up there? N minus 1. So I'm going to do minus 1 plus 1. Yes. Right? I'm going to do minus 1 plus 1.
Complete the squares.
Now, sum n equals 1 to infinity. I'm going to break that into two different numbers. The first number is going to be 1/10 to the 1, and then the other one is going to be 1/10 to the n minus 1. Do y'all agree that this is the same thing? Right? I mean, that's the